Good day, everyone. Today we will explore the fundamental concepts that underpin the critical aspect of thermodynamics. It's all about the energy balance for closed systems. We are from Group 6. Welcome to our journey through the fascinating history of energy balance in closed systems. In the 17th and 18th centuries, when pioneers like Boyle, Hooke, and Amontons made groundbreaking discoveries in gas properties and temperature, scientists of the time developed the theory to explain heat transfer that flowed into and out of objects during heating and cooling. Fast forward to 1824, when Sadi Carnot introduced the concept of a heat engine operating in a closed cycle. His work laid the groundwork for the second law of thermodynamics. In the 19th century, the first law of thermodynamics emerged. It's a fundamental principle that energy cannot be created or destroyed in a closed system, but can only change forms. This law is expressed as delta U is equal to Q minus W. In 1843, James Joule's experiments demonstrated a quantitative relationship between mechanical work and heat energy. In the 19th and 20th centuries, Clausius, Kelvin, and Planck contributed to the development of modern thermodynamics. Their work refined our understanding of energy transfer, heat engines, and closed systems. In conclusion, the principle of energy balance in closed systems, rooted in the laws of thermodynamics. In thermodynamics, we uncover a guiding principle that called the energy balance for a closed system, deeply rooted in the first law of thermodynamics. Energy flows in and out is total energy change. Delta E, which represents the system's exchange of energy with its surroundings as heat, Q, and work, W. There's also kinetic energy. Delta K, a potential energy, delta PA, and internal energy, delta U, that influence delta E. It's the balance that determines whether our energy grows or shrinks. The difference between Q and W, symbolized as Q minus U, remains constant. Path independence is the unchanging thread in the energy balance narrative, regardless of the system's path. In summary, the energy balance for a closed system is a profound principle in thermodynamics. It's ensuring that total energy remains constant. It accounts for changes in kinetic, potential, and internal energy, all driven by the exchange of heat and work. For the equation part, we assumed EK is 0 and IP is 0 since these two energies are neglected. So the final equation will be delta U is equal to Q minus W. The change in internal energy tells us how much the total energy within the system has changed during a process, due to changes in temperature, kinetic energy, potential energy, or any other form of energy. The Q and W terms represent the energy transfer mechanisms. When heat is added to the system, it increases the internal energy of the system, making it warmer. Conversely, when work is done by the system, it reduces the internal energy of the system. The key insight here is that the equation demonstrates the conservation of energy within the closed system. It's neither created nor destroyed, only transformed between different forms. In summary, the first law of thermodynamics, captured by the equation delta U is equal to Q minus W, is a powerful tool for understanding energy dynamics in closed systems. The first law of thermodynamics states that in a closed system, the total energy remains constant. This means that energy cannot be created or destroyed within the system. It can only change forms. Both heat and work represent energy in transit, moving in and out of the system. In simple terms, any energy added to the system through heat or work results in an increase in the system's total energy, while energy leaving the system causes a decrease. Last but not least, we can conclude that the theories of energy balance in closed systems revolve around the principle of energy conservation, energy transformation, and the transfer of energy through heat and work. Here's the example question of energy balance for closed system. This is the mathematical calculations to solve the problems. For container A, final temperature is 567.74 Kelvin. Since container A is at constant pressure, final pressure is equal to the initial pressure, which is 0.5 megapascal. For container B, final temperature is 665.86 Kelvin. To calculate the final pressure, we can use the formula of ideal gas. PV is equal to nRT. By rearrange the equation, we have the constant volume V is equal to T over P. Then we can get the final pressure for container B is 1.11 megapascal. This is the solution using MATLAB. These are the three-dimensional models related to our topic and the example. These are the references we used to complete this assignment. Thank you for watching.